So my talk today is about different approaches to RAG. I think, so yeah, I guess a bit of background on myself. I'm a data scientist. I worked at Meta for a number of years before moving to Optum. I'm facing kind of, I guess, large enterprise problems now with a lot of documents. I think they're very similar. They happen across a lot of different companies. And my hope is that there's a lot of aspirational founders in the room that want to solve these type of problems. So I'm hoping there's some relevance either in your jobs or in your companies for this sort of talk. But what I found, I guess, over the last year or so is that, look, I think if you have to do any sort of query to your vector store, your knowledge base, your first port of call is often to implement some kind of RAG. This is me, because it's not Secret Santa. But I put this code up on GitHub. I vibe coded it on Sunday in a couple of hours. It seems to mostly work and kind of tells the story about what I want to do. But if you haven't come across RAG before, basically you have a document store, you create a set of embeddings out of that document store, and then a user will submit a query. That's all right. A user will submit a query, and then you'll return the top K by cosine similarity. So it'll compare the user's query to your document store and retrieve the most similar results. Some of the shortfalls of this, well, I think when you're actually using the embedding process to create your document store. Oh, sorry. It's, do you know, when you're doing a live demo, you think, yeah. These secrets. I thought the issue even I coded the live demo. It doesn't seem. But anyway, there's the problem is that you often miss very specific information because RAG has, like, I guess, a tendency to summarize or cast over. Just based on cosine similarity alone, you're going to miss some information. So if you're extracting very detailed information, like maybe token-specific information, maybe you're looking for a specific number in a contract or something like that. Standard RAG approaches can like systematically miss this. So if you've ever had the frustration of like querying your vector store for some piece of information and you haven't returned it, you're like, why is it missing? One of the common approaches is to go off and do a bunch of like chain of thought reasoning or reprompting or selecting different top K and sending that through again. Kind of had mixed success with that. So one solution to that problem is to use a graph structure instead. And I think graphs are, very common in machine learning, but what I'll present here now is just how we can, that's the cinematic, yeah. How we can use the graph to, it's kind of freaking me out, to be honest. You can turn it down a little bit, maybe. Yeah, it's like, am I a bit stoned or something? Yeah, so anyway, back to graphs. That's perfect, yeah. So yeah, you can use a graph to do this. So graphs are made up of nodes and edges. You can kind of create your nodes a few different ways. I used an example here where I just pulled the attention is all you can need paper or sections off it. So that's what's in here, but you could just, any sort of PDF loader or any document loader would work that. And it does scale to very large PDFs like multi-thousand pages or document stores. So this is just like, we're going to take the paper here and create some chunks and embeddings out of it. Standard what you do for RAG so far. So it's after creating 23 chunks out of that. Obviously it's a toy example because you can see the just pieces of text from that particular paper, whatever Claude responded when I asked. And you create your chunks in a standard way. I just want to get down to the RAG sort of implementation. Basically, when you submit a user query, it takes the cosine similarity of the user query in your vector store and then returns top K. You can specify whatever the K is. And then you can use that to present some summary to the end user, or else use it in like a chain of thought or something else like that. So that's all very standard, and that has all the problems that I just described. So this is just using whatever the free embedding model was in Collab, so it's all mini L6v2, but it works for any sort of embedding model. And I want to get down here. So yeah, this is your user query is like, how does the attention work in a transformer architecture? You see your top 5, top K results come back, and then you can put that into your processor, your code base, whatever. The problem is that often misses information. So Graph RAG's approach to maybe how would you capture some of that information and make sure that you actually have what you need. So this is some handy vibe coded illustrations of what embedding space looks like. I think I'll kind of skip by that. And this pairwise, I didn't ask for either of those. Here's kind of where graphs can kind of come in. So if you're familiar with graphs, they are constructed of nodes and edges, but often we use kind of like standard out of the box edge algorithms. And what I found is kind of useful is like if you define your specific edge algorithm the same way you would anything else, instead of like you can use cosine similarity as one of the weights in that algorithm, but you could also do regex pattern matches or some sequential mapping or something else. The point is that you can have like a multifaceted retrieval algorithm for your edges and then use that in the graph rag to improve your responses. So here the custom weight edge algorithm takes in your semantic similarity, which is your cosine, the structural similarity and in the actual PDF, and then also sequential similarity. So assuming like you can kind of flip the direction on that last parameter, and say if you wanted to prioritize say chunks that were further away in distance in the document, you can multiply that by -1 and so on. The point is that you have flexibility in how you're constructing that. So you can kind of come up with that. So this is just an equi-weighted edge algorithm based on those concepts, but the takeaway is that you can put in whatever you want there when you're calculating that. So there is some nice demo at the end here where it goes through the same process. And this is a kind of cool data science thing. You can look at you have so many more options to look at the distributions in your data when you have like multi-weighted edge algorithms rather than just semantic similarity, where you might look at this type of distribution, but you can see how like, those distributions are different. So in theory, you're capturing more information there straight off the bat. So yeah, this is what your knowledge graph looks like. This is pretty standard. I guess we're all kind of familiar with these. Maybe we're not, but there it is anyway. And there's one last thing I want to check. So yeah, you send the same user query, but you get a bit of a different output. When you're sending your user query, the difference is that you'll specify a number of hops. So you create your chunks, and you can kind of call them your nodes from the get-go. And then you want to see what the connections are between the nodes. So when you're running your query, you can specify the number of hops, or so the number of nodes in the graph that you're going to traverse. Obviously, the more nodes you specify, it gets more. You get a lot more O of n. So it kind of scales. Pretty nastily. If you went out to 10 hops, like you're going to crash your system fairly quickly. But the point is, you have the opportunity to capture more information when you're looking across different nodes. And this is the piece de resistance of the whole demo. But I think, tell me it runs. Yeah, it does, yeah. Thank God for Opus. This was actually really cool. So I'll just play this as like, we can pause it. So there's your basic query. That's your initial semantic search. And then see how much extra information is captured in, say, hop 1. So you can, based on whatever edge algorithm, specify how you want those nodes to be connected. Like if you're trying to ingest a big long legal contract and some of the clauses are separated by 1,000 pages, you can specify a connectedness of those two nodes and then retrieve it in your query and then take the next step in your LLM process. So I found this really helpful, like when you're trying to run an automated process end to end and you're really looking for the right information in your context window without overloading it with like a 1,000-page PDF. What I found is, like, even though say the frontier models will say that the whatever million token context window, you often suffer for this lost in the middle problem. If there's a very specific token or rate or number or something in the middle of it, you're going to lose it. So this gives you a way to kind of iteratively traverse the graph and pull in the relevant information you want. So you can do a lot of experimentation with that specific edge algorithm. I'll just play this last fancy graph. This is comparing RAG versus standard RAG versus graph RAG. And what you'll see is that your semantic similarity is after returning the top 5 chunks or nodes, and that may or may not have the information that you need. But by using the multi-hop, you can kind of encapsulate all the information in the graph. So you can see in this particular toy example based on that paper, it's after catching one additional chunk, but it's a very small paper. So you'd imagine how that would scale if you had a massive document store with thousands of PDFs, or if you had a lot of information that you have. So you can kind of, the point is, it gives you another parameter to play with, that your retrieval is accurate and it's returning exactly what you want. So I think that's a pretty solid approach to this problem. And it's not too much more computationally expensive if you just use a couple of hops. And if you're kind of a bit clever with how you define your edges, you can actually get a lot of information out of this. So yeah, I think that code's on GitHub, so feel free to pull it or mess around with it, but it does work. So and I think that the last graph is just before Alessandro's told me to stop, is just comparing the type of information you get. Again, it's a toy example, but it does pull back different information, and it gives you extra, like maybe if you wanted to even evaluate your RAG system, you could use a graph approach to just see if you're capturing all the relevant information. So I'm happy to answer any questions on that. if you want to pull the repo, be my guest. I'm very happy to share any learnings I've had from it. So.